Hello everyone, welcome back. In today's lecture, we will discuss only two topics. The first one is how to find an area using double integral. Second one is change of coordinate, that is how to solve a double integral by changing the coordinate. And I will discuss, of course, both of the topic by considering the problems on lecture 35 from tutorial sheet. So let's begin. Okay, and the first page itself only I have considered lecture 35 class problems. There are 4 problems. We'll handle each and every problems one by one. The first 3 problems are based on to find the area enclosed by the curve, and the last problem is the double integral problem by changing to polar coordinate, that is change of coordinate. So there is one simple formula to find the area using double integral. What is the formula? Formula for area is simply double integral over dr. If this r is a region whose area is to be evaluated, then this particular formula we will use. So I will illustrate the procedures and methods with the help of one problem. So in fact, I have considered a problem from tutorial sheet. We are asked to find the area of a plate in the form of a quadrant of the ellipse. So a quadrant means there are in fact 4 quadrants. So we wish to find the area of the quadrant of the ellipse. So you can easily see this is an equation of ellipse. So first thing we will do is we'll draw an ellipse. Okay, these problems are not difficult. That's what I'm not going to discuss in depth each and everything. Simply what you have to do is area formula is this, where R is this region, shaded region R. Now you have to integrate over this region. Okay, one important thing, what you have to integrate is a unit function. Okay, this is the formula for finding area. There is no function is equal to 1. So as you know how to integrate, you have to integrate in order to cover this whole region. So how will we cover this? First of all, I want to integrate in y direction. So y direction, as usual, y equal to 0, that is this line to this curve. You have to vary y. So y equal to 0 to, on this curve, what is the value of y? You will get it from this equation. What is the value of y? Once you integrate in this direction, second is to collect all these vertical strips from where to where? From x is equal to 0 to x is equal to a, so that you will cover up whole region. Okay, this is exactly same as what we have already discussed. So dy dx, first you integrate dy, integration of dy is y. Oh, okay, it is slightly, it is not a misprint, but do not misinterpret this statement. Lower limit is 0 and upper limit is b by a under root of a square minus x square. Substitute the limit, you will get this expression. Again you integrate this, so integration is this much, and substitute with the limits, you will get pi ab by 4. And if you wish to find the area of a whole region, you have to multiply this area by 4, that is pi ab is the area of an ellipse. I hope this is clear. Now here is another problem which you are asked to find the area between the parabola this and this. Now first of all, I will draw the parabola y square equal to 4ax. The lower one is x square equal to 4ay is lower parabola, and another one is the upper parabola. So we have to find the area. Again formula is same, area equal to dr, then limit is only our concern. I wish to first integrate in y direction. So integrating in y direction, what is the value of y on lower curve? Listen to this carefully. What is the value of y on the lower curve? Lower curve value of y is x square by 4a. And what is the value of y on the upper curve? So upper curve is under root of 4ax. Once you integrate in this direction, collect this black color arrows, that is vertical strips. From where to where? From extreme this point to extreme this point. This point is 0 and this point is 4a. Well, if someone have a doubt regarding why this x is equal to 4a, I want you to do this as an exercise, how to find this intersection, so that this x will be equal to 4a. Now again same rule, integrate with respect to y. So substitute the limit for y, you'll get this much. Then whatever remaining quantity is in terms of x, and do substitute the limit for x, simplify it, you will get this as the answer. Again, okay, this is slightly different from the previous problem. So here is to find the area of a cardioid, but over here the problem is not in Cartesian coordinate system. Now here is one very important and beautiful concept which you have already discussed. You will revive it one more time and you will use it over here. Now this problem is slightly different from above because this is in polar coordinate system. The formula for an area in polar coordinate is as follows. Now listen, there is a different formula for finding area in case of polar coordinate system. So area will be here, not simply dr, but one extra quantity will be there. I hope you can guess what is this j. J is a Jacobian of transformation. When you transform from Cartesian to polar, if you can recall my previous lectures, that Jacobian is used as a scaling factor when you transform some dimension from one coordinate system to another coordinate system. So over here this j is that scaling factor. Okay, so this is the formula for polar coordinate system, because in case of polar coordinate system you can again go back and recall that Jacobian chapter. So Jacobian for polar coordinate system is r, so this r will come extra. So you can note down formula for finding area in case of polar coordinate system is this one. Okay, but remaining everything else is same. To find the area over here now you have to be careful while dealing with this geometrical part or geometrical interpretation of the problem. So you may get confused, that's it. So let us take it easy. So up to this quantity I'm not going to discuss again because it is integration over r dr. Now what about the limits? So first I want to integrate along r. Now exactly same way we integrated y equal to 0 up to some variable on the top I mean on the above side. So same is over here. When you integrate from r equals to 0 to where r will vary up to, you see, as you vary theta there are different values of r. For instance, r is 0 at theta equal to 0. Now r is a when theta equals to pi by 2. R is 2a when theta equals to pi. So r is a function of theta. That means r vary from 0 to this curve. Okay, I will repeat, r vary from initial point 0 to this curve, whole curve. So what is the value of this curve? Value of this curve is a1 minus cos theta. That is r value on that curve is a1 minus cos theta. This is limit for r. Now once you integrate, you imagine the n number of these arrows coming out of origin and ending up to this curve. Then second part is just to collect those arrows from where to where. Now here you have theta, so theta vary from 0 to pi. Okay, so second is 0 to pi is a value of theta. Now this inner integration part, I think it's not necessary to discuss everything. Well, here is a small misprint that I missed a small quantity over here, that is a bracket, I guess should be closed, and there should be, it's difficult to write but I'll try, d theta. Yeah, it's nice. So if you integrate this, you'll get your answer. So one more time, it is a change of coordinate. Before solving the last problem of lecture 35, I want to introduce you this change of coordinate. Sometimes what happen is some function will look very complex and difficult in one coordinate system. We will simply change it to another coordinate system. Function will become easy. For instance, if you consider this f of xy equal to x square plus y square in Cartesian coordinate system, what will happen in polar coordinate system? That is, replace this, do this transformation. Suppose let me call this f as g in polar coordinate system, then g will be equal to r square. You see, compared to x square plus y square, r square looks much, simple. Okay, this is the advantage, or there sometimes we have to change the coordinate in order to simplify our problem. So before we proceed further. One again the same topic, that is Jacobian. You need to understand, if you have a small dimension over here dx dy and you change the coordinate into uv system, over here is xy coordinate, you change it to uv system, then that small package, that is the elementary area, will no longer remain as du dv. Instead, one more extra quantity will come, that is Jacobian. So this is the use of Jacobian or application of Jacobian here. Okay, integration over here, integration of f of x by dr will change to integration. Now f, we named it as z because it will take a different form, which will be function of u and b. And this particular region r, this is just for understanding purpose only I made it. It may not happen so, but over here it is kind of a elliptic area. When you transform it, it turns to be a rectangular kind of thing, which I named it as S. So R changes to S, F changes to G, and this dr changes to J into ds. This part is what I want you to focus on. Okay, this is only something extra we have to work on while solving the problem by changing the coordinate. So we'll have a look into one problem on this topic. So here is the problem. You are asked to evaluate this integral by changing it into polar coordinate. Problem is very simple. Transform the Cartesian code to polar. This is a transformation. X equal to r cos theta, y equal to r sin theta. Then Jacobian of above transformation, I have worked on this part over here. Jacobian is equals to r. This function, let me call it as f, will take the form this. Then all you have to do is set the limit. Now it is understood this y is equals to 0 to this y is equals to this quantity. This is exactly same as what we have discussed in our previous video, that this limit actually is a limit for a circle. Y is equals to 0 means this line, and y square equal to x square, y square plus x square equal to a square. This above part is your circle, but since x vary from 0 to a only, so it will give us a first coordinate of a circle. You need to understand this, otherwise you won't be able to solve the problem by changing the coordinate. This geometrical explanation is important here. I will repeat this again. Have a look. Y is equals to 0. So y equal to 0 is this line. So y is equals to this quantity. If you square it, you will get y square plus x square equal to a square, which is a circle. So the above line is your circle. Okay, above line is your circle. This to y equal to 0 to this, that is semicircle, but we are not done. We cannot conclude it is a semicircle. We have to check the limit for x also. So x vary from 0 to a. Okay, this is not even a semicircle because x vary from x is equal to 0 to x is equal to a, this much. So this is a first quadrant. It's 1/4 of a circle. This is the area we have to cover to integrate. Now we change this thing into polar coordinate, so it will look somehow like this. This is the full integration which changes to polar coordinate. So I'll discuss the limit later on. First of all, function will change into this part. Okay, I have worked over here. F is this and function in r theta is this. So this is the function, and this is Jacobian into dr d theta. Now limits. Limit are very simple here because r is a radius which is a constant. R will remain fixed here. R is a. So r equal to 0 to a, and what about theta? Theta has to vary from 0 to pi by 2. Then further is simple integration. I hope you can explore this integration. Okay, so you guys try to solve the homework problem, and in case of any difficulty, you can contact me either individually or you can message me in a group as well. Okay, thank you.